Hello, and welcome to the Honeywell Avionics Familiarization Webinar for AgustaWestland's AW139 Phase 7. My name is Rob Erlick with Honeywell's Flight Technical Services, and I will be speaking throughout this webinar. This webinar will first cover a summary of Honeywell customer support contacts, additional training offered, and information about very useful resources which can be found on our new website, pilots.honeywell.com. After showing you what's available by Honeywell in terms of support contacts, training, and additional resources and documentation, we'll go into each of the new features offered with Phase 7 of the 139. From there, I'll cover all of the Phase 7 improvements. I'd like to reference myself as a primary point of contact for Honeywell support on FMS and avionics issues for the AW139, as well as our Aerotech support team, which can be contacted for any issue as well at aerotechsupport@honeywell.com. Additionally, this summer, Honeywell has launched our Pilot Gateway website, which can be found at https://pilots.honeywell.com. Here is a short summary of the training available through Honeywell Training Solutions and CAE. There is a 4-day EPIC line maintenance course which covers systems, hardware, database loading, central maintenance, and ESD module handling. As mentioned, our new Pilot Gateway website, found at pilots.com, provides pilots with a variety of resources summarized here. Our login page uses the same ID and password as other Honeywell websites. New users can register for a Honeywell account, and pilots who are not sure if they want to register can take a tour. Publications available to users include the following: alerts and updates such as the NAV database content letter, removed procedures, documents and resources such as pilot guides, familiarization guides, service information letters, sales bulletins, pilot training videos, navigation alerts, and newsletters. Additionally, you can get technical support from our Contact Us page. And the Contact Us page serves 3 functions. Questions. You can ask general questions. Feedback. We would very much appreciate any feedback you might provide on Honeywell products, services, and on pilots.honeywell.com, which will help us continue to improve for your needs. Technical issues. You can report technical problems here and ask for assistance as well. Now let's discuss new features as well as improvements with Phase 7. In this section, I'll discuss TCAS 7.1 or TCAS-II, which is an option with the Phase 7 upgrade and only available for the long-nose version. ADS-B out, LPV approaches in general and how LPV is implemented with Phase 7, new Missed-Approach defaults, which provide LNAV coupling at go-around, RNP approaches in general as well as what the improved graphical display for Phase 7 looks like, and the Symbology, full-time DME, changes to default callouts for EGPWS, changes to the landing gear oral warning, and changes which will aid maintenance checks by use of the collective on the ground. Let's start then with TCAS-II, otherwise known as TCAS 7.1. To review, TCAS is an independent airborne system for coordinating traffic separation. It is primarily designed to be a backup to ATC. TCAS detects unsafe traffic conflicts with other transponder-equipped aircraft and displays their symbology on the multifunction display, or MFD. Keep in mind that it only detects other aircraft with transponders installed and on, and therefore will not display any aircraft which is not properly utilizing its transponder. Finally, TCAS-I refers to a system which only displays traffic advisories, whereas TCAS-II provides resolution advisories. Continuing with our review of TCAS, let's look at how surrounding aircraft are interrogated and relative positions and trajectories computed, and then we'll take a look at how the symbology is depicted. TCAS can interrogate other aircraft transponders squawking modes A, C, and S, basically all required transponding modes. And again, TCAS will not detect any aircraft which do not have their transponders turned on. The TCAS interrogation reply enables the system to compute the range between your aircraft and that which is being interrogated. It also computes the bearing to that other aircraft as well as the altitude, the intruder's vertical speed, and the closure rate. With the TCAS-II or 7.1 option of AW139 Phase 7, the pilot will have resolution advisory symbology as depicted in the current slide. Of course, the pilot will still receive traffic advisories and alerts as depicted from TCAS-I. But with TCAS-II, a resolution advisory will be visually depicted in a color scheme on the vertical speed tape to the right of the PFD. The red colored area denotes the avoidance zone, while the green colored region indicates the fly to zone. TCAS-II for the AW139 is only available for the long-nose version, since it is not certified on the short-nose variant. The vertical speed digital readout is not displayed when a TCAS resolution advisory is present. You probably noted that the previous slide showed both. That's a file photo from our pilot guide and is a demo picture which will show all the PFD advisories in Symbology at once, not depicting an actual scenario. There are two types of resolution advisories. Preventive. A preventive resolution advisory instructs the pilot to avoid certain deviations from the current vertical speed. A preventive up advisory displays a red down avoidance zone from the bottom of the vertical speed tape. A corrective resolution advisory instructs the pilot to deviate from the current vertical speed to avoid the intruder. A corrective down advisory displays a green fly-to band at the down advisory's recommended descent rate, and a red up avoidance extends from the top of the fly-to band to the top of the vertical speed tape. It is possible to have a preventive down advisory and a preventive up advisory at the same time. For simultaneous up and down preventive advisories, there is both a red up avoidance zone and a red down avoidance zone with a green space between the two zones which looks like a fly-to band. When an intruding aircraft is detected, oral and visual traffic advisory alerts are displayed. Traffic is displayed in the upper left-hand corner of the attitude sphere as shown. The traffic display flashes for the first 6 seconds and then shows steadily. With TCAS-II, alert displays are related to resolution advisories. When a resolution advisory is active, a red traffic annunciator is displayed in the upper left corner of the sphere. With the red and amber traffic annunciators active, the red traffic annunciator is displayed. In other words, the resolution advisory takes priority on the PFD. When TCAS-II is installed, the transponder mode is TA only. A white TA only annunciator is displayed. When the vertical speed fails, an RA fail annunciator is displayed beneath the other TCAS annunciators. Additionally, if TCAS fails, the amber or red traffic annunciator will not be displayed and the TCAS fail annunciator will appear. Since we're on the subject of TCAS, let's review TCAS in general on the MFD in the next few slides. TCAS traffic settings are displayed in the lower right corner of the MFD map. They provide a TCAS target filter status: normal, above, below, or expanded. When the absolute altitude mode is selected, flight level is enunciated. The default setting is relative. Absolute altitude settings will revert to relative mode after 15 seconds. When a TCAS traffic advisory is indicated, the cursor moves to the MFD specifically on the map menu button, and if the map window is opened, a traffic advisory appears as a filled amber circle as depicted. The 2-mile range ring is displayed when traffic is selected on MFD. And just as depicted on this slide, a ring of 12 small circles define the 2-mile radius around the helicopter icon. Within that 2-mile radius ring are additional dots arranged at each clock hour position. This graphical TCAS arrangement is removed when MFD map range is 25 nautical miles or greater. Additionally, for TCAS-II, you will note that the TCAS window does not range in using the automatic scale expansion seen with TCAS-I when the traffic advisory penetrates the 2 nautical mile range ring on the map display. This is intentional and per the requirements of DO-180. Now let's take a quick look at TCAS target type symbology. The orange filled in circle is a traffic advisory indicating the intruding aircraft is potentially hazardous, with the closest point of approach at 15 to 30 seconds. The filled in blue diamond means proximate traffic, or PT, indicating the intruding aircraft is within plus or minus 1,200 feet and within a 5 nautical mile range. Finally, the empty blue diamond means other traffic, or OT, indicating that the intruder aircraft is greater than plus or minus 1,200 feet or beyond a 5 nautical mile range. A no-bearing target readout will show as amber data located above the TCAS status window. This means that the intruder with a transponder is received, but TCAS is unable to determine the bearing. In the no-bearing target readout, the first line contains the highest priority no-bearing target data, and the second line contains the second highest priority no-bearing target. Down at the bottom of the slide, we see the vertical speed symbol, which is indicated when the intruder aircraft vertical speed is 500 feet per minute or greater. This is displayed as a vertical arrow in the direction of the vertical speed. This slide concludes the TCAS portion of this webinar. So let's now change gears and talk about ADS-B. In Phase 7, the AW139 will be equipped with ADS-B Out. ADS-B Out is part of the FAA's mandates as well as that of many other international regulatory agencies. So in the coming slides, we'll discuss what is ADS-B. Automatic Dependent Surveillance Broadcast, or ADS-B, is a function that allows an aircraft in the air or on the ground, or for that matter any other vehicles including surface vehicles, oil rigs, etc., to automatically broadcast information without interrogation from a remote source such as radar or TCAS. It is dependent surveillance in the sense that the information depends on a suitable GPS position source, This information is used by Air Traffic Management System to surveil and control the aircraft in the airspace. As the name implies, the information that is being output is continually broadcast to anyone with a receiver. ADS-B out is the transmission of this information at 1-second intervals. ADS-B uses a dual link system, UAT or User Access Transceiver, and Mode S or 1090 ES for extended squitter. UAT is intended for general aviation. It reduces 1090 congestion and the cost of equipage. UAT broadcasts on 978 MHz and is only used in the United States below 18,000 feet. The 1090 MHz extended squitter uses the extended Mode S transponder. It can be used in all airspace and will be required above 18,000 feet and internationally. So in summary, the system transmits ADS-B out messages only. It does not receive messages. ADS-B is certified to DO-260B on the AW139 to comply with the FAA 2020 mandate. ADS-B equipped ATC facilities, thus using ADS-B in, can see radar-like displays of traffic updates in near real time, and the updates do not degrade with distance or terrain. It provides broadcast data with respect to the aircraft position, aircraft state data, and aircraft vector data of high frequency and accuracy over the 1090 MHz transponder, and the only action the pilot performs is to verify the system is on. That will conclude the ADS-B section of this webinar. In this section, I'm not only going to discuss the LPV capabilities of the helicopter, but provide a brief overview of the system upon which it relies. First, we'll discuss that ground and satellite-based system, then LPV approaches in general, and after that, we'll see what they look like in the cockpit as we fly an LPV. So let's look at some important acronyms you'll see time and again. SBAS refers to the Satellite-Based Augmentation System. That is the ICAO term for the regionally specific versions like EGNOS, the European Geostationary Navigation Overlay Service, which is the SBAS for Europe, WAAS, the Wide Area Augmentation System, which is the SBAS for the United States, and of course other regions have theirs, Japan's MSAS, for example. Finally, LPV stands for Localizer Performance Vertical. SBAS, known in the U.S. as WAAS, was jointly developed by the U.S. Department of Transportation and the FAA. It was part of the Federal Radio Navigation Program circa 1994 to provide performance comparable to Category 1 ILS for all appropriately equipped and certified aircraft. The FAA and the aviation community wanted to use the global positioning system for precision approaches, saving money on ground infrastructure and allowing precision approaches to many more runways. To increase the accuracy of GPS in order to support precision approaches, the solution has been to use a correction signal generated by ground sensors and transmitted to a GPS receiver. More specifically, that solution is to transmit the correction signal from a geosynchronous satellite called now a Satellite-Based Augmentation System, or SBAS. In addition to being able to do RNAV GPS approaches to lower minimums, the other benefits to SBAS include eliminating the predictive RAIM check requirement by EASA's AMC 20-4A and FAA's AC 90-100A. The system is 10 times more accurate than traditional GPS, yielding better position accuracy. The system uses GPS altitude instead of barrel VNAV, which is much more consistent and not susceptible to incorrect altimeter settings, temperature, and altimetry errors. This means the pilot can ignore temperature limitations when conducting an LPV approach. The picture on the right shows various decision height capabilities along the glide slope, based on the GPS accuracy designed into the approach structure. GPS, GPS barrel VNAV, SBAS, and an upcoming improved system called GBAS, which I will not be covering in this webinar. Here is an approach plate for Charlotte, North Carolina, RNAV GPS runway 18 left. It shows 3 different published minimums, the LPV, the LNAV VNAV, and LNAV only minimums. In order to use the LPV minimums, the aircraft must be equipped and authorized to use SBAS. If conducting the approach to LPV minimums, the temperature restriction does not apply. If conducting the approach to LNAV VNAV minimums, the temperature restriction for barrel VNAV must be followed. Note in this slide of an approach to Toulouse, France, that European GPS approaches with LPV minimums will have slightly different formatting, but the LPV nomenclature will be consistent. The VGP LPV is very similar to an ILS glide slope. Just like the ILS VGP LPV glide slope, known as the NGS or pseudo glide slope, will not level off at decision altitude. It'll aim about 50 feet over the runway threshold. It will provide a stabilized approach path. It allows standardized approach procedures and looks like an ILS, and have a published decision altitude which allows for a momentary dip below minimums during the missed approach. LPV approaches in general allow for the following capabilities. They provide the highest precision GPS SBAS enabled instrument approach procedures currently available without specialized aircrew training requirements, such as the RNP AR. The landing minima are similar to those in an ILS, with a decision height of 200 feet and visibility of a half a mile. The landing minima are similar to those of an ILS, with a decision height of 200 feet and a visibility of 1/2 mile. And they are designed to provide accuracy of 2 meters and availability above 99%. Now let's talk about LPV approaches in the 139 specifically. The following are some key points about setting up an LPV in the AW139. As you will see, when selecting RNAV approaches in the FMS, LPV is the default approach minima type. The FMS navigation database contains the final approach segment, or FAS, data block associated with the LPV minimums. That FAS data block is transmitted from the FMS to the GPS SBAS landing system sensor unit referred to as the GLSSU. It computes aircraft lateral and vertical deviations for the final approach segment. With LPV enabled, the GLSSU displays LPV deviations and distance to the landing touchdown point, or the LTP, on the primary flight display known as the PFD, and provides such information to the flight director in lieu of ILS guidance. To fly the LPV approach, select FMS as the navigation source. LPV mode armed will use the flight director modes and enunciations with LNAV, VGP when outside of the approach area, and NLOC or pseudo-localizer and NGS or pseudo-glide slope when inside the approach area. You must still pre-select the first altitude for the published missed approach procedure, but that can be done earlier upon capturing the approach, since the LPV approach altitudes are acquired from the final approach segment data block instead of your pre-select altitude settings. The aircraft will descend on the LPV approach to the missed approach point with no pilot actions. Now let's take a brief look at setting up the approach. As mentioned earlier, and as you can see in Figure 7-2 from the AFCS Pilot Guide for the AW139 Phase 7, when selecting RNAV as the approach type, the approach minima type page will show the LPV option as the default underline select key 1L. When LPV is the selected approach minima type, the system gives the following indications. On the arrival page, as seen in Figure 7-1 from the same AFCS Pilot Guide, RNAV min will show LPV. The LPV approach channel ID and reference is displayed below line select key 2R and should be used to confirm that the FMS database approach matches the published instrument approach procedure. As you will see in the coming slides, the approach enunciator is displayed on the PFD when the aircraft enters the approach area. We'll cover setting up the LPV approach again once we get to the section of flying the LPV, but first, let me go through some more information about how the LPV works with this aircraft. The LPV uses GPS data for both lateral and vertical guidance. As shown previously, select the LPV approach on the FMS. As with other approaches on this FMS, you must select either approach or DCL on the guidance controller in order to arm the approach. Within 40 nautical miles, the LPV enunciator is armed on the PFD, showing white letters on a black background. Within 2 nautical miles from the final approach fix, the enunciator transitions to LPV Active, indicated by green letters on a black background. Also note the approach identifier information on the PFD. It's another opportunity to confirm you have the correct approach programmed into the FMS. Let's do a quick look at the approach indications and related parameters. You'll see the color coding is consistent with other approach modes. The LPV is armed, indicated by white letters, when the aircraft is within 30 nautical miles of the landing threshold and there is a valid final approach segment, or FAS, data block loaded into GPS, and the related SBAS system is operational. LPV is active, indicated by green, when a valid final approach segment data block is loaded in one of the 2 GPSs and the FMS is using GPS calculated final approach segment deviations to determine guidance. LPV is unavailable, which is indicated by amber, up to 30 nautical miles of the landing threshold when conditions exist that would prohibit descending to LPV minimums during an approach. The following are conditions that can cause it to activate. A warning of a loss of SBAS corrections after the LPV approach has been loaded, or warning of excessive lateral or vertical deviation, which is 2 dots, from the approach flight path after passing the final approach fix. An LPV unavailable CAS message will appear if the system is unable to perform the LPV. The white LPV symbol indicates the system is sourcing information from the FMS for navigation. The green LPV symbol indicates sourcing from the GPS. And the amber LPV symbol indicates the system is unavailable and is sourcing the FMS for all information. If the LPV sourcing data is lost, you'll see an LPV unavailable CAS message, amber LPV display on the PFD, and an amber X on the right side of the PFD as depicted. Once the aircraft is within 2 nautical miles of the final approach fix, the LPV Active or green annunciator appears on the PFD. Lateral and vertical deviations now change from FMS to GPS source pseudo ILS deviation signals. NLOC, or the pseudo localizer, is enunciated as the lateral flight director mode. The NLOC mode arms after LNAV is captured and localizer capture criteria is met. LNAV disengages and NLOC transitions from armed to captured. The approach annunciator, approach, or DCL is displayed to the right of the waypoint identifier. And finally, a small L is displayed inside the vertical deviation pointer showing the aircraft on the glide path, similar to an ILS glide slope. NGS, or the pseudo glide slope, is the active collective flight director mode when the following occur: when NLOC is captured, when the glide slope capture criteria is met, and after VGP disengages. As the LPV approach continues and the aircraft approaches the runway threshold, a transition to a radio altitude of 50 feet is initiated and a 50-foot hover is held. When the flare maneuver has begun, LPV is disengaged as auto level captures at 150 feet AGL. NGS is replaced by auto level. However, you'll normally see NLOC disappear at about 70 to 80 feet AGL. And finally, an amber X is displayed on the vertical deviation scale. Concerning LPV Abnormal Indications. If the GPS is unable to perform the approach, the LPV annunciator is replaced with an amber LPV. An amber X is displayed on the vertical deviation scale as well, and the airport ID and approach ID will flash amber. In the slide example, you can see the WAAS identifier W24A to the right of the airport identifier KPND, and a CAS message indicating 1 or 2 LPV unavailable is displayed. In this case, the flight crew should either terminate the approach or, if in the terminal area, change the approach minima type to LNAV VNAV and use LNAV VNAV or LNAV minimums as appropriate, or choose to fly another approach. Note that the 1 or 2 LPV unavailable CAS message is not displayed below 80 feet AGL. For a missed approach with LPV, the pre-select altitude can be set to the first missed approach procedure altitude, and the aircraft will descend to the missed approach point without pilot input. As I mentioned previously, the LPV vertical guidance comes from the final approach segment data block. Activating missed approach automatically engages LNAV and is initiated by either pushing the go around button on the collective control grip, selecting missed approach on the CDU, or inputting a direct to for a non-approach waypoint. Following a missed approach command, the LPV annunciation is removed and the airport ID and approach ID are replaced with the RNP value, and the lateral and vertical deviation pointers are sourced from the FMS. Now I'll go through setting up an LPV approach and demonstrate what you will see on the primary flight display as the aircraft captures the VGP. Within 2 nautical miles of the final approach fix, VGP drops and LPV is captured. In our scenario, we're going to fly an LPV approach to Deer Valley, or KDVT, specifically the RNAV GPS to runway 07 right. Here are the approach details. The LPV minimums are 400 feet AGL or 1779 MSL. We are to be no lower than 3,900 feet MSL at Bowles, and we will follow the glide slope no lower than 2,900 feet MSL at CGAP, the final approach fix. That means we should be on a VGP coupled approach until approximately 2 miles from CGAP, the final approach fix, which is when you will see the LPV become active, along with NLOC and NGS as VGP and LNAV drop off. Also note from the missed approach procedure that 5,000 feet MSL is the first published altitude. Setting up this approach, select Arrival from the nav page 1 of 2 on line select key 6R. Next, from the Arrival page, select the approach prompt at line select key 2L as you confirm you have the correct airport KDVT selected. In the approach page, you see RNAV 07 right in line select key 1L, which is the approach we want to fly for this demonstration. On the next page, select the point of transition for RNAV 07 right. In this case, we want to select Banyo, line select key 2L. Finally, select Activate. Note that anytime you have programmed an LPV approach, it is shown first under the RNAV min option prompt at line select key 2R. If LNAV or VNAV are preferred, line select key 2R would allow you to change from LPV to another such approach minima. So here, our flight plan has been input and your MCDU should show, as does the photo on your left. Intercepting Banyo and on a 3-degree glide slope after intercepting it at C-gap and finally terminating at runway 07 right. On the right, we see the approach diagram from Banyo to runway 07 right as planned. Starting out, the aircraft position is 11.9 nautical miles from ASNP, which puts us just 0.1 nautical miles from Banyo. The cruise altitude was 6,000 feet, and you can see LPV is armed. Airspeed is at 100, and the aircraft will have decelerated to 90 indicated airspeed for the approach. Also note the airport WAAS identifier to confirm again we are on the correct approach. The aircraft is now 6.8 nautical miles from Bowles, and VGP is now armed. LNAV is active, and the airport WAAS identifier information at the lower left of the PFD has turned magenta, confirming the approach is now active. The airspeed is 90 knots, and altitude still at 6,000 feet. As you can see, a decision height of 400 feet AGL has been dialed into the decision height window. Now with the aircraft exactly 6 nautical miles from the final approach fix, C-gap, VGP is captured, which means the system is now vertically coupled. The system will bring the aircraft into an eventual 3-degree descent on the glide slope. The pre-selected altitude can then be set to 5,000 feet, which is the first altitude of the published missed approach. The glide slope indicator now shows a magenta P, and we're descending 450 feet per minute through 5,020 MSL. Having just passed Bowles, the aircraft will soon turn left to 074 degrees to C-gap. At less than 2 nautical miles, actually 1.8, to the final approach fix, we now see by the reverse video LPV symbol indicating that LPV is in the process of capturing, as is NLOC, the GPS-driven localizer. The glide slope has now converted from VGP magenta or captured P to a magenta or captured L to indicate the data is now derived from the LPV and the final approach fix database. Altitude is now 3,460 feet MSL as we continue our descent at 500 feet per minute. A few seconds later, as we have only advanced 0.1 nautical miles, we see LPV captured and VGP is now replaced with a reverse video of NGS. 0.3 nautical miles later, you can see the PFD with LPV completely active, showing NLOC, NGS, and LPV. As the arrow shows from the diagram, we are now 1.4 nautical miles from the threshold and at the published decision height of 400 AGL. After another only 0.3 nautical miles, the aircraft is 1.1 nautical miles from the runway. The min indication shows an amber at decision height, and the pilot has activated the go-around by either selecting it from the FMS or pressing the go-around button on the cyclic, which automatically initiated a command for a 1,000 feet per minute climb. At that point, all LPV data is dropped, NGS, NLOC, LPV, and replaced with go-around, GA, to advise that the go-around mode has been activated. Finally, within 0.1 nautical mile from when we pressed go-around, we see reverse video of GA and of LNAV indicating LNAV is now capturing. Once active, the system will provide us with a laterally coupled missed approach procedure. Since vertical is no longer coupled, Alt-A will get us to the first missed approach altitude, since, as you can see, we have 5,000 dialed in already. Now you've seen the PFD indications for an LPV approach to the missed approach point and LNAV activation with go-around. The following scenario assumes DCL is selected instead of approach in order to demonstrate the visual indications of an approach to runway threshold using the DCL approach mode. This approach is to runway 33 at Martin State Airport in Baltimore, Maryland. The decision height is 390 feet AGL, and the final approach fix is Cindy. The PFD shows we are at 5.8 nautical miles from the final approach fix, Cindy, for runway 33 at Martin State in Baltimore. DCL has been selected instead of approach and is capturing. LPV is armed and LNAV is coupled. Note the WAAS identifier in the lower left of the PFD. The left side PFD here shows we are now 2.1 nautical miles from runway 33. The LPV approach is active, showing an active decel mode, which set the aircraft to decelerate to a default airspeed of 80 knots, shown in magenta above the speed tape. You can see NLOC, NGS, and a magenta L for the glide slope. The right side PFD shows us 0.6 nautical miles from runway 33 at 247 feet AGL, which is below our decision height of 390 feet. Airspeed shows us decelerating through 90 knots as we get ready for auto level to arm at 150 feet AGL. As depicted in the left side PFD here, The aircraft, already at its target 80 knot decel speed, has gone below 150 feet AGL, engaging the auto level. Note that NLOC is still engaged and NGS has dropped off. You'll normally see NLOC uncouple around 80 feet AGL. On the right side PFD, the aircraft is at 95 feet AGL. NLOC is still a few feet above the altitude at which normally disengages, and we are 0.1 nautical miles from the runway threshold. As the approach continues, the aircraft will continue to decel until reaching a hover of 50 feet AGL above the runway threshold. In this section, you've seen how LPV appears on the PFD from the initial approach fix through the final approach fix to go around, as well as through the decision height to landing. So let's revisit and discuss a bit more on the LNAV go-around feature. Prior to Phase 7, the AW139 go-around mode put the aircraft to wings level and dropped all lateral flight director modes, as well as initiating a 1,000 foot per minute climb. With Phase 7, there's an automatic LNAV coupling at go-around without any pilot interaction other than pressing the go-around switch or selecting Missed-Approach on the FMS. And then the system will automatically sets the display to FMS, whether on an ILS, VOR, or other non-FMS sourced nav mode. In other words, when FMS is not the nav source, the go-around mode switches to FMS on the pilot's HSI automatically. In addition, it arms the LNAV mode to couple laterally with the flight director. Next up is Required Navigational Performance, or RNP. In this section, I'd like to discuss not just the Phase 7 improved graphical display of RNP and EPU information, but review terminology, RNP concepts in general, and to provide a bit more detail as to how RNP functions and what some of these numbers mean to you, the operator, in terms of clearances, requirements, and capabilities. RNAV is the method of navigation that permits aircraft operation on any desired flight path within the coverage of ground or space-based navigation aids, or within the limits of the capability of self-contained aids, or a combination of these. An RNP is RNAV operations with onboard navigation alerting and monitoring, and to identify for the pilot whether the operational requirement is or is not being met during an approach. FTE is the flight technical error, which is the path tracking error introduced by the pilot's or autopilot's ability to utilize displayed guidance information to track the desired flight path. Total system error is the combination of EPU plus FTE, and EPU is the estimate of position uncertainty, which is a statistical estimate of the navigational system position uncertainty displayed in nautical miles. Now let's review the RNP approach in general. An RNP is essentially an RNAV approach. It provides additional level of precision, flight path repeatability, and procedural design flexibility. Aircraft with RNP capabilities have onboard avionics with the capability to keep the aircraft within the airspace specified by the RNP requirement. This approach type provides a number of advantages to both pilots and controllers due to the design flexibility, accuracy, and repeatability, which allows precision type approaches on a lateral level around either congested airspace or difficult terrain. So let's talk about the improved graphical display of required navigation performance, or RNP, and estimated position uncertainty, or EPU, for FMS approaches. The center triangle represents the FMS lateral deviation to course centerline. The horizontal line represents the EPU as an error bar with winglets, or vertical lines, which indicate the sum of the EPU and flight technical error, or FTE, which must remain within the RNP to ensure obstacle containment. When the EPU error bars or winglets reach 2 dots, the aircraft would potentially be exceeding the RNP value. Error bars expand and contract depending on the uncertainty level. This RNP lateral deviation scale, as it is called, should be displayed in the approach or missed approach phase of flight. Below, in this slide, is an example of an exceedance. Even though the flight crew can monitor the individual contributors to lateral position error, it is the total system error that must be monitored to ensure the aircraft is meeting the required navigation performance. It is important to know that the EPU cannot be controlled by the pilot. The pilot can only control the aircraft's position to the centerline of the approach, or flight technical error, FTE. The TSE is the sum of the EPU and FTE. The TSE is displayed as the lateral deviation of the winglets to the CDI centerline, as shown in the depiction. The flight crew must monitor TSE to ensure the navigation performance requirement of 3 times the RNP is being met. In that case, 2 dots is RNP, 1 dot is 1/2 RNP on the CDI. Note that the AW139 is not certified or capable of conducting RNP AR approaches which require additional equipment, as well as FAA and pilot certification. AR, or Approval Required, RNP approaches are capable of an even tighter accuracy, but since this is not a topic for the AW139, I will not cover it in this webinar. It is of note to understand that an RNP procedure can be differentiated from an RNP AR procedure by the chart name RNAV GPS for our RNP on the AW139 versus RNAV RNP for an RNP AR. The RNP value indications are still displayed with Phase 7, and they are in the same place, to the left of the HSI, when the following occur. When the FMS is selected as the primary nav source, when the FMS indicates the Mark on Target, or MOT, maneuver is inactive, and the ICAO reference, path identifier, and LPV annunciator are not displayed. The RNP lateral deviation scale, along with the RNP EPU lateral deviation pointer, will be displayed near the bottom of the ADI sphere on the PFD when the following conditions are met. When LNAV is engaged on the on-side flight director, when HSI is in full compass or arc mode, when the FMS indicates that MOT is not captured, and when the aircraft personality mode or APM parameter indicates that the RNP limits display is enabled. To review, the maximum deflection scaling is adjusted per the RNP values set in the FMS, and the RNP lateral deviation scale color will be magenta or cyan, depending on the source, and turns amber if the EPU and FTE exceeds the RNP limit. In summary, the FMS incorporates the RNP concept to monitor and enunciate the performance of the navigation function. For each phase of flight, a default RNP value is defined but may be edited for certain procedures or airspace. That editing can be accomplished via the RNP page through FMS Progress Page 2. To fly RNP approaches, the pilot must ensure the aircraft maintains the required RNP throughout the approach. And finally, the AW139 is not certified or capable of conducting RNP AR approaches, and that an RNP procedure can be differentiated from an RNP AR procedure by the chart name, which is RNAV GPS versus RNAV RNP, which is the designator for the RNP AR. That concludes the RNP section of this webinar. Another additional feature provided with Phase 7 is a full-time DME capability. DME distance and ident are displayed on the PFD regardless of whether or not the FMS is the primary navigation source. On aircraft prior to Phase 7, DME distance is displayed only when FMS is not the selected nav source and in the same location as the FMS distance. Additionally, Phase 7 has added SAR and offshore inhibits to optimize EGPWS functions for the oversea operation. Tail strike alerts are reduced by improving the existing performance curve based on actual performance. Nuisance alerts over water are reduced to provide additional position integrity labels, which allows the EGPS a more accurate altitude calculation. And the too low gear oral, which duplicates the monitor warning function, is eliminated. For more details about the Mark V EGPWS or other models, you can find the Honeywell website and access manuals and other documentation by typing Honeywell Installation and Design Guides Mark V, as seen at the bottom of this page, into a Google search menu. One of the issues faced by operators prior to Phase 7 was that the landing gear oral warning sounds too late for oil rig operations, sometimes only after the aircraft is over the helipad. That software logic uses radio altitude of less than 150 feet AGL as the trigger. For Phase 7, the software logic is modified to monitor the ground speed as well as the radio altitude. Therefore, if either radio altitude is less than 150 feet or the ground speed is reduced to no less than 30 knots, the pilot will hear an oral landing gear warning if the landing gear is not down. As an improvement, mainly for maintenance personnel, the collective servo drive can be engaged for testing and operational checks on the ground. On aircraft, prior to Phase 7, the collective cannot be driven with weight on wheels, in other words on the ground. Phase 7 provides a CMC test to drive the collective on the ground for ATP support and troubleshooting, and is used to validate collective operation and appropriate levels of friction on the collective control. So far, we've discussed the main features added for the AW139 Phase 7. In addition to those features, many in-service issues reported by pilots have been addressed. Next, we'll look at a list of those. Phase 7 has improved the functionality of previous models by addressing the following issues. Radar altitude hold mode won't hold altitude, various FMS issues, DC generator and main and auxiliary battery fluctuation, trim issues, decision height flashes and goes invalid, ILS offset, fly-up collective safety activation, and avionic fault CAS message. More details and a summary of each fix follows. Radar altitude hold, or RHT mode. Operators have advised that radar altitude hold mode does not hold altitude in some circumstances. Upon reaching selected altitude, the aircraft may slowly depart from that altitude and in some cases continues until the oral altitude call-out is heard. Honeywell Engineering found a bias in the acceleration feedback, which has been corrected in the AFCS software. In this slide is a list of FMS software issues addressed and corrected for Phase 7, along with the Honeywell Service Information Letter, or SIL, number as referenced. In this slide is a list of FMS software issues addressed and corrected for Phase 7, along with the Honeywell Service Information Letter numbers, or SIL numbers, as a reference for more information about that particular issue. At the bottom of this slide is a website address for online access to these Honeywell SILs. In addition, you can access SILs on our Pilot Gateway site referenced in the beginning of this webinar. We'll pause here for a few seconds to allow for screenshots for future reference. Another issue reported from operators is one concerning DC generator values flickering. Operators were seeing fluctuations of the DC generator values when the current value was close to 0 amps. They were also reporting false DC gen caution CAS messages. Honeywell Engineering discovered that the input values were similar in magnitude in millivolts to noise, and the existing software was unable to evaluate that input. The fix improved the software to better filter that noise. Similar to the issue with flickering generator values is the issue with the main and auxiliary battery load fluctuations, reportedly fluctuating between 0 to -7 amps DC. Similar to the DC gen issue, the root cause was identified as a combination of noise and small offsets at lower input values. So we improved the input filtering, and that has corrected the problem. In this issue with trim faults, operators reported that the trim system was failing with a trim fail CAS message in flight with the autopilot engaged. Honeywell Engineering discovered that the trim monitor logic tolerances for the CAS message were too strict, so the logic was modified to better distinguish a real fault and avoid nuisance faults. The issue with decision height involved the preset decision height number flashing when going to amber dashes at around 300 feet AGL. The decision height would return once again, descending back through 3,000 feet AGL. Honeywell discovered that this was due to software being previously modified in Phase 5 to address nuisance rad-out failures. It turns out that this change affected the decision height functionality, and this was also corrected in the software for Phase 7. The issue with the in-flight collective was reported by operators after a continuous descent through 2,500-foot AGL. The fly-up function was reported to have erroneously intervened, raising the collective with height limit, or HTLM, displayed on the PFD. The cause was that the fly-up collective safety function was incorrectly activating. The AW139 RFM has been updated with this issue, and it is addressed in the AFCS software for Phase 7. The commonly discussed ILS Offset has also been addressed and corrected in Phase 7. Operators have reported that while on the localizer, the aircraft will offset to one side of the localizer and will remain offset for the remainder of the approach, regardless of pilot inputs. Honeywell Engineering found that in some circumstances, the course error was being washed out, thus resulting in a bias with respect to the desired track. This has been corrected in the AFCS software for Phase 7. Finally, there has been an issue reported with an avionic fault CAS message appearing at power up on the ground, which would clear up upon takeoff. To address this problem, Honeywell and Augusta recommend following the troubleshooting procedures from the Interactive Electronic Technical publication. If further assistance is needed, we recommend you please contact your Augusta Westland technical representative or Honeywell technical support at aerotechsupport@honeywell.com. That concludes this webinar for the AW139 Phase 7 Changes and Improvements. I've reposted our contact information on this last slide and encourage attendees to contact myself or our Aerotech Services Group for any concerns, and visit our Pilot Gateway website for additional resources to improve your knowledge on a few of the topics addressed here, such as SBAS, LPV, as well as for RNP. Tutorials can be accessed as well as pilot guides, pilot FAM guides, and the service information letters, or SILs. Thank you for your time and attendance.